happy World Quantum Day, so we can all celebrate that. Now, today, we are going to go on a trip together. We are going to journey into a world where the strange becomes normal and where what happens might challenge what we think is or is not possible. Because today we are going to travel together into the world of quantum mechanics. Now, quantum mechanics is the physics of the tiniest building blocks in the universe, atoms and subatomic particles, which are way, way, way too small to see. But these teeny tiny particles, they are the basic building blocks of everything in the universe. They make up big things like planets and stars, living things like dogs and trees, non-living things like rocks and guitars, the air we breathe, everything. Which means that those tiny, tiny particles, and the physics that governs them, quantum mechanics, it really governs absolutely everything we see in the universe at its most fundamental level. And to understand that just a little bit more today, we're going to have to talk a little about energy, electromagnetic energy, that is. So all objects, they absorb and they give off energy in the form of radiation, electromagnetic radiation. Now that includes things like the visible light that humans can see, the invisible heat or infrared light that our bodies give off, and the ultraviolet light. That's the reason we put on sunscreen when we go outside on a sunny day. And all of those different kinds of light travel in waves. And each of those waves has sort of a characteristic size or wave length. Now, the waves that are over here on this side, that have kind of a longer, more lazy wavelength, they carry less energy than the waves that are all the way over here that are bouncing up and down really quickly. They carry more energy. And for a really, really long time, this wave nature of light was the only way that scientists understood how light worked. But 100 years ago, in the early 1900s, some discoveries were made that changed everything. One of the most important discoveries about light energy came from this person. Does anybody know who this is? Yes, Albert Einstein. I've heard it from several people. And one of the things that he discovered was that light does not just behave like a wave, it also behaves like it's made up of tiny particles called photons. Now, photons are little packets of light, and they carry a very specific amount of energy. So, for example, if we look just at the visible part of that electromagnetic spectrum, a photon of blue or purple light carries more energy than a photon of red or orange light. And it's a little like these measuring cups. Like if you could imagine that I only have two choices with each of these cups. I could fill it up to the very, very top or not at all. Then that's the kind of energy that in that case you could see that the blue photon will always carry more energy than the orange photon. And things that have a specific amount of energy like that, either full or empty, they are called quanta. That's the plural part of the word. If a singular form of quanta would be a quantum, as in quantum mechanics. And this discovery of quantized energy, it opens the door to lots of other kinds of discoveries. So for example, has anyone here ever seen a rainbow? Raise your hand. Or a sun catcher in the window that makes rainbows on the wall? Yeah. So in each of those cases, the crystal in the sun catcher or the water droplets in the air, in the case of the rainbow, are doing exactly the same thing that a prism does when you shine light on it. It is splitting that light out into all of the beautiful colors or spectrum of the rainbow. Now, if you were to take a gas of an element like neon and heat it up so hot that it's glowing, that also is giving off light. And if you were to shine that light on the prism, you would get something a little bit different. So let's compare those cases. Here we have our prism with our ordinary visible white light, splitting that out into all of the beautiful continuous spectrum of the rainbow. And now if we do the same thing with our light from our heated up, very hot, glowing gas, instead of all of the colors of the rainbow, what we might see is just these few colored bands of very specific colors. And this was a big mystery when this was discovered. But in fact, each and every element or kind of atom in the universe has its own very specific set of those colored bands. And that is so unique to each and every element that we can use it sort of like fingerprints to tell what kinds of atoms or molecules we have in different materials. So for example, that's exactly what astronomers do when they try to figure out what distant stars or planets are made of. They are looking at the light, the spectra of the light, coming from those distant objects to try to figure out what elements are in those distant objects. Now, but nobody really understood why each atom or each kind of atom had its own unique band of colors until this person figured it out. Does anybody recognize this person? It's a little less famous than Albert Einstein, maybe, but this is Niels Bourne. He was a physicist working on trying to understand what atoms are and how they work. And he was looking at these atomic spectra in order to do that. Now, here is his model of the atom. You may have seen something like it before, where there is a nucleus, the blue dot in the middle, and around the nucleus, there are electrons, like the red dot, orbiting around the nucleus in this big circle. And Niels Bohr's big idea was that what if those electrons, they can't orbit any old which way around the nucleus of the atom. They have to stay at very specific distances or energy levels away from the nucleus. And they can only be at those distances. What would happen then? In that case, we could give an electron a little bit of energy, and maybe it could hop up to a new energy level. Or we could take a little energy away and it could hop down to a lower energy level. But it could never, ever exist in between those two energy levels. It just can't happen. How do you give an electron energy anyway? Well, we know that light carries energy, so maybe we could shine a light on our atom, and the electron could absorb that light, take that energy from the light, and use that to hop up to a new energy level. But it would have to be exactly the right amount of energy to go exactly from one energy level to the next. And because, as we saw before, the amount of energy carried by a photon is directly tied to its wavelength or color, that means it has to be exactly the right color of light in order to be absorbed. We could try shining a different color of light on our atom, but if it's not the perfect amount, if it's not the perfect color, it won't be absorbed and it'll go right through. It has to have just the right amount of energy to be absorbed. Now, what happens when an electron loses energy? Well, it's kind of similar in that case. That energy has to go somewhere, and it's emitted as a photon. And again, because it's going from one energy level at a very fixed amount to another energy level at a very fixed amount, that energy carried away has to be a very specific amount or color of light. So what we're seeing when we see those colored bands is just the colors that are being emitted by electrons as they are moving between energy levels in that particular kind of atom. And we don't see any of the other light. So this solved a big mystery of physics. And way back, almost 100 years ago, a whole bunch of physicists got together at this big conference to try to figure out what that all meant. This was the beginning of the first quantum revolution. A new field of physics was born, and a new era of discovery began. And a lot of things that have been discovered about the quantum world, they may seem a little bizarre to us, a little strange, but you have to remember that this is the way that the universe works at its most fundamental level. And it's just not what we're used to because we don't see these effects on the human scale. One aspect of the quantum world that is very cool, but a little strange, is wave-particle duality. Do you remember how I said that light is both a wave and a particle? Well, the same is true of matter, things made of atoms. The particles inside atoms, like electrons, also behave like waves. But what is wavy about something like an electron? Something like a particle that seems like it should be a ball bouncing around. What could be wavy about that? Well, let's go back to our model from Bohr of the atom, and remember that he said that the electrons are orbiting the nucleus in these big, neat circles. We actually know now that that's not completely true. There are electrons around the nucleus, but instead of orbiting like a planet orbits the sun, they actually exist in this fuzzy cloud around the nucleus. And it's a cloud of probability. There is only a chance that the electron is in any one place at any given time. Let's take an analogy on the human scale. Let's imagine that you had just arrived at the Museum of Science, so we're not too much of a stretch here. But when you first got here, I would have no idea where you were in the museum. You could be in any level, you could be in any exhibit, maybe you have some preferences. Maybe there is a 30% chance that you're in the engineering design workshop, and a 10% chance that you're in Arctic Adventure. And I'm being really generous by saying maybe there's a 60% chance that you're right here listening to me give this presentation on stage. But those preferences, they might change over the course of your visit, going up and down like a wave. Where the peaks of the wave are higher, that's where you're more likely to be. And where the peaks of the wave are lower, that's where you're less likely to be. This is very similar to what we see on the quantum scale. So quantum particles, like electrons, they are actually waves. And in the sense that the wave is a map of the particle's existence. Where the peaks of the wave are higher, that's where you're more likely to find that particle. And where the peaks are lower, that's where it's less likely to be. But here's where things start to get a little different between the quantum world and the human scale. In our human analogy, I could actually see you right now. So there is a 100% chance that you are sitting right here. But even before I could see you with my own eyes, you were definitely somewhere. That is not the case with quantum particles. It is not just that we don't know exactly where the particle is. It's not that we don't have enough information. It's that it really isn't in any one place at any one time. The trick is, it changes once you observe it. So as soon as we observe that particle, the wave collapses, and it becomes just a particle in one very definite place. But when you're not looking, it exists as this fuzzy cloud of chance around the nucleus. So that might make you think, well, if there's only a chance that the electron is in any one place, does that mean it's anywhere at all? Is it nowhere? It's actually kind of everywhere, all at once, all at the same time. And to demonstrate, here is a model of an electron, a quantum particle. And I'm going to give you a fact about this electron. It can exist in one of two states. And I don't mean New York or Massachusetts. I mean it could be in an upstate, or it could be in a downstate. And actually, until you observe this particle, it is up and down and everything in between, all at the same time. And this is called quantum superposition. Now, if I were a quantum particle, I might be up here on stage and sitting out there with you in the audience at the very same time, which would be a little creepy. So I think I'm glad I'm not a quantum particle. And if that is just a little too weird for you, well, you would not be alone. One person in particular really struggled with some of the implications of quantum mechanics. Everyone remember him? Einstein. Why was Einstein not buying it? Well, one of his big discoveries or breakthroughs was the idea that nothing can travel faster than the speed of light. Which means, in theory, there is a limit to how quickly something could travel from point A to point B. Or is there? When Einstein and his colleagues, they started to dig into the mathematics behind quantum mechanics, they discovered something we now know as entanglement. Now, this is a link that can exist between quantum particles that allows them to affect each other's behavior instantaneously, even if they're great distances apart. So let's say we have two entangled cats. Now, really, cats can't be entangled. This is something that happens on a much, much smaller scale. But cats are great, so let's pretend that we have two entangled cats. And they cannot see or hear or communicate with each other in any way. But nevertheless, because they are entangled, they affect each other's behavior instantaneously. So if one stands up, the other sits down. No delay, no communication between them. And the strangest thing is that you could separate them by huge distances. You could put them at opposite ends of the universe, and they would still affect each other's behavior instantaneously. And this was just a little too much for Einstein. He thought it was very strange, and he called it spooky action at a distance. He struggled to see how both his theory about the speed of light and entanglement could be correct. Although today, we know that those are actually not in contradiction. So like we all are sometimes, he was wrong. Entanglement is real. How do we know it's real? Well, first of all, we have tested it experimentally time and time again, using everything from tiny, tiny diamonds to huge telescopes, collecting light from the early and distant universe. For another thing, we've built technologies that require it to work in order for the technology to run, and it does. So, for example, rather recently, scientists have used entangled photons to teleport information from Earth to space. And all of these successes, all of these experiments have actually led to quantum mechanics being called the most successful theory in all of science. Which brings us to today, because we are in the midst of a second quantum revolution, where a new wave of quantum physicists are harnessing those strange properties of superposition and entanglement to create a new wave of quantum technologies. So, for example, that satellite I just mentioned, that teleported information, that is the beginning of a new quantum communication system, which will one day allow us to share information from around the world while keeping it safe from hackers. Another kind of technology that you might have heard of is the quantum computer, which is a special kind of computer that people are working on right now that one day may be able to harness the power of entanglement and superposition in order to make calculations very, very quickly, much more quickly than even the most powerful supercomputers can do it today. And big companies all around the world, like IBM and Google and Microsoft, they are racing in order to be able to come up with the first truly useful and viable quantum computer. Now, these are not going to replace your laptop anytime soon, but they are going to be really, really useful in fields that require intense computation. So things like climate modeling, drug discovery, artificial intelligence. They're also going to really be helpful in understanding more about the inner workings of atoms themselves. So one day, quantum computers will help us understand more about the quantum world that they are built on. So from the last century, quantum mechanics has gone from this radical new debated idea to this incredibly precise theory, and it describes the fundamental and surprising nature of our universe. So welcome to the new quantum revolution. And I will just put this website up here again to wish you one more time a very happy World Quantum Day, and I'd be happy to stick around and answer any questions that you might have. Enjoy the rest of your time at the Museum of Science.